Molweni guys, hello. I hope you guys are good. Um, I'm fulfilling a topic request from a comment sections. Saying, yabo. The request was, can I please do a lesson on superposition and Thevenin's theorem N4. This is for N4s. Firstly, I'm going to start with superposition theorem. Okay, so let us first read what does the theorem says. Okay, the theorem is saying in any multiple source network, the resultant current in any branch is the algebraic sum of the currents that would have been produced by each source acting separately. Okay, so this theorem is telling us about a multiple source network. So it means that when we are applying this theorem, guys, we have to have at least two sources or more. Okay, so let me interpret what is being said in this theorem. Let's say here is our network. Okay, you see that we have our two sources, which I've marked with yellow. Then the second source, which I have marked with red. You know? We see that both these sources are contributing to to make a resultant current in this branch. Okay, for example, I1 is coming from this source and contributes. Okay, then I2 is coming to this from this source and contributes to this current in this branch. Okay, you see, the resultant current is flowing in this branch. Okay, that is why, okay, this theorem is saying to us now, the resultant current in any branch is the algebraic sum of the currents that would have been produced by each source acting individually. Okay, suppose here is a hypothetical case now. Let's say uh, let's say you see this tank. This is let's say this is tank A, the yellow one. The red one is tank B, this one. Both these two tanks have certain level of water. Ne? Okay. Let's say we pour water from tank A, and then we pour water from tank. Oh, sorry. Oh, sorry, guys. Uh, the red one. Sorry, the red one is tank B. Sorry. Let's say we pour water from tank A, this one, into this bigger tank. Then we pour water from tank B. So we want to know the purple color I'm using as this purple tank. I'm using the purple color to show the resultant amount of water that it will be in the bigger tank. Okay, we want to know how much, what is the total, how much liters of water is in the bigger tank. And for us to calculate that, what we do, let's say this yellow tank had 10 liters. This red tank had 15 liters. Okay, meaning which if I know how much each tank contributed, I can actually calculate the resultant, which is gonna be uh, 25 liters. Okay, 10 liters, which is coming from the yellow tank, uh, uh, 15 liters, which is coming from the red tank. So this is superposition, guys. What we are doing, we are calculating how much current is delivered by each source separately. Okay, we do that separately. Well, in other words, we first remove one source from the circuit and replace it with a short circuit. Let's say I want to calculate how much current this source VA, this one, how much current it contributed to this resultant, sorry, to this, sorry, yes, sorry, to this resultant branch current. Okay, so what I'm gonna do is I'm gonna first, meaning what I'm gonna do is I'm gonna first isolate this one and remove it from my circuit. Then I calculate how much VA contributed. For example, okay, sorry. So I'm gonna say now, sorry, let me use yellow, okay, to show that I'm dealing with source A. Okay, to show that I'm dealing with the source A. Okay, source A, which is 5 volts. Okay, it has an internal resistance of uh, 4 volts, which is, we say R1 is equals to 4. Oh, sorry, it's 4 ohms. Sorry, 4 ohms. Okay, then, okay, okay, then, sorry, then we come here. And we said we're gonna remove source B because we are interested in knowing how much did source A contributed to this I3. Okay, okay. So I'm gonna short circuit. Okay, this red color is show that there was a source here. I short circuited it because I want to analyze each source acting separate. Okay, okay. This is remember. Okay, sorry. This guys is an internal resistance of this source. You don't remove resistances. You only remove the sources by putting a short circuit, please. Okay, it is sorry, it is R2 6 ohms. Okay, this one is R3 now, which is 8 ohms. Okay, what I want to calculate is I want to calculate this current, okay, I3 due to A, due to the source. That is why I'm saying I3A. This is due to the source. Okay. Remember again, the current that is coming here is I1. Then let's say let's name this current I2. Okay, guys, this I2, uh, let me emphasize this. This I2 that is in this circuit is not the same as this I2. This I2 is coming from this source. This I2 that I've placed here is coming from this source. It's not the same as that one. Please, be confused. The main objective here is to uh, try, sorry, the main objective is to try and determine I3A, this is gonna give us the amount of current that this source contributed to this uh, branch current here. Okay, so the first thing I can do is first calculate the total uh, resistance of the circuit. And once I've calculated the total resistance, I can calculate the total current of the circuit is I1, because I1 is the total current which splits in this branch, then recombines back again here and becomes I1 again. It's the total current. So how do I calculate the total resistance? If I look here, let me use a different color just to highlight. This resistor and this resistor are what? Are in parallel, guys. Okay, so let me calculate R parallel 1. R parallel 1 is equals to, uh, let me use the product over sum rule. Okay, which is R3 times R2. R3 plus R2. Okay. When I calculate that, let me punch that. Let me substitute first. It's 8 times 6, 8 plus 6. Okay. Hope you still guys still see. 8 times 6 over 8 plus 6. That is 3,429 ohms. Okay, let me use the highlighter again. Now that I've calculated this parallel combination, I see that this parallel combination is gonna be in series with this resistor. It's gonna be in series with this resistor, meaning I can now calculate R total, which is R total is equals to R1 plus R parallel 1 plus R parallel 1. Okay, which is which is R1 is 4 ohms, 4 plus 3,429, which is gonna give me 7,429 ohms. Okay, now that I've found the total resistance, I can get this total current so that I can apply the current divider rule. Yeah, okay, now I can calculate I1, which is equals to VA over RT, which is 5 over 7,429. That is gonna be, or I1 is gonna be 0,637 amps. Okay. Then now that I've calculated I1, I am able to calculate uh, this current that is contributed by this source. okay, using the current divider rule, which is gonna be I3. I3 A means that this is the current. Let me go back to the original circuit. This is the current. This is the current value that voltage source A contributed to this branch current. Yeah, okay, which is gonna be uh, R2. Remember, current divider rule. Mali current elapha, you say you use the resistance of the other branch, and current divider rule only applies to two components in parallel. You must remember that R2 plus R3 times I1. I1 is the total current, so which is gonna be 6 over 6 plus 8 is times 0.637. That is going to be 0.288 amps. Okay, this means, guys, this source is contributing. This source is contributing 0.288 amps in this branch. And so what does that mean in terms of my analogy? It means that in terms of my analogy, it means that this bucket is contributing. It has a 0.288 liters. I'm making an example that is contributing when we pour it in this bigger basket. Okay, guys. Now that you have determined a contribution source A, and source A, this one, to this branch current, and we now have to determine a contribution source B. How much is source B contributing to this branch current so that we know the total current in this branch? Yabo. That is what is superposition. Yabo. Let us treat each source acting separately. And then we calculate how much current is contributed by one source and then by the other source. Then we combine those current algebraically so that we get the current that is flowing in this branch. Now we're gonna calculate uh, current how much current is this source contributing to this branch current. Okay, when we do that, it means that we have to short circuit now this source. Okay, which brings us to the second stage of this calculation. What we are doing now, we are calculating um what we are calculating I3 due to the second source. Okay, due to the second source. Then at the end, what we're gonna do, we're gonna add these two current that is contributed by source A and the second one which is contributed by source B. So, okay, let us draw our circuit. Okay, okay. 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 Mm-hmm. Okay. Remember now we said we are short circuiting source A. Let us short circuit to source A. Fine. And okay. We leave its internal resistance. Okay. Uh, and this resistance is an internal resistance of source A. Remember your original circuit. There is a resistance elapane. Okay. Continuing. Okay, let us write the values. Okay, this source must be between, they said it's 7 volts, which is source B, sorry. Um, R2, sorry, which is equals to 6 ohms. Then we have R3, which is equals to 8 ohms. Then we have R1, which is 4 ohms. Okay, so a source current is sugar upper, that let's call it I2. Then let's call this one I3, and due to source B. Okay, this is the current that we are looking for, because this current is the contribution of this source to this branch, sorry, to this branch current in the original circuit. Okay, and remember another current that is flowing, let's call it I1. Guys, this I1 is not the same as the I1 in the original. It's not the same as the I1 in the original question, in the original circuit. This I1 is due to this source, hence it is flowing in that direction. It is not flowing in the right direction, it's flowing in the left direction. Okay, so I need to find this current. Obviously I'm gonna use the current divider rule, but for me to use the current divider rule, I need to know the total current of the circuit, which is I2. I2 is the total current of the circuit, because I2 comes from the source, gets to this junction and split into I3B and I1. Okay, so how do I find that? I have the voltage now. Now I need to calculate the total resistance of the circuit. Okay, what I see here, I see that this resistor and this resistor are in parallel. So I first calculate the parallel branch. R parallel 1 is equals to R1 times R3, product over sum rule, R1 plus R3, okay, which is gonna be equals to 8 times 4, 8 plus 4. That is gonna give us, let me punch on the calculator, 8 times 4 over 8 plus 4. That will give us 2.6 ohms. Then remember now we haven't finished. Okay, we have calculated this parallel combination. This parallel combination is in series with this. Sorry, this parallel combination is in series with this resistor R2. So we get R total. R total, the circuit is R2 plus R parallel 1. Sorry, plus R parallel 1 is R2 plus R parallel 1. R2 is 6 plus 2,6, which is gonna give us 8,6 ohms. 8,6 ohms. Okay, which is gonna give us 8,6 ohms. Okay. Now that we have found a total resistance, we can actually now sorry nje kancinci. We can now find a total current, which is I2. I2 is gonna be 7 volts over, RT is 8,6 now. Okay, 7 over 8,6. That is gonna be that is gonna give us 0,814 amps. Okay. Now that we have calculated I2, which is our total current, we can use the current divider rule to find this current. Okay, I3, which is the current that is flowing through I3 due to the source. And that's gonna be okay, R1 over R1 plus R3 times I2. Okay. That is 4 plus 8 times times 0,814 amps. Okay. The current that is supplied by the second source, which is VP, to that branch is, let's punch it. Yeah, sorry. It's 4 over 4 plus 8 times 0,814. That is gonna be 0,271 amps. Okay, guys, we have found how much each source contributed to that branch current. For example, we have found now that that this bucket contributed, we have found that this bucket contributed it contributed 0,271 liters, for example. Now, what is the total? If we look at here now, the current from this source, okay, let me use green. The current from this, the current from this source flows and comes to this junctions, and the current from this source also flows to this junction. They combine and flow in the same direction. Because they flow in the same direction, it means we have to add in order to get the resultant. Okay, it means we have to add in order to get the resultant, guys. Uh, so the resultant, which is I3, is equals to I3 contributed by the first source plus I3 contributed by the second source, which is 0,288 plus 0,271. Okay, then we get I3, okay, which is 0,288 plus 0,217. That is gonna be equals to 559 milliamps. Guys, what we're seeing here is that um, this theorem allows us to calculate a current in any branch whereby we have multiple sources. Yeah, well, so if we have two or more sources, we can actually implement this superposition theorem to calculate any current in a particular branch by treating each source independently. We treat each source independently. We want to calculate how much current this the first source contributed to that branch that we seeking current in, and how much current is the second source contributed to that branch current we are looking for the current in, and so on and so on. What I'm gonna do is this was an example question. I'm gonna implement this superposition theorem in an actual exam type question. Guys, now that you know everything about superposition, I've picked a question up from a question paper. I think it's July 2018, if I'm not mistaken. But study the circuit below and calculate the current flowing in the 7 ohm resistor using superposition. Okay, where's that current? This is the current. Sorry, this is the current they're talking about. A flow in that junction. Okay, so we said it must be superposition. You have multiple sources, two or more sources now, of which is, let me say, my first source. Let me use the red color. Nanzina. Okay, the second source I'm using blue. Nans. Okay, so we want to calculate how much current is contributed by this source to this branch current. Okay, then how much current is contributed by this source again to this branch current. Okay, the best thing that you would have to do in this question is first simplify these two parallel combination. What do I mean? Okay, let's simplify that circuit. Okay, okay, let's call this R parallel 1. Okay, uh, okay, then let's call this R parallel 2. Okay, this is your V1 now. Okay, okay, this is your R3, which is equals to 7 ohms. Now, okay, then here is your second source. Okay, Okay. This is V2, which is equals to 24 volts. Then this is V1, which is equals to 12 volts. Okay. Okay, I said must let us first simplify here. Let us first simplify this two. Anna. Okay. Kasi simplifier, we get that OR parallel 1 is equals to product over sum. These are two in parallel. It's R1 times R2 over R1 plus R2. So that is 6 times 4. That is 6 times 4. 6 times 4 over 6 plus 4. Okay, let us punch that on our calculator. 6 times 4 over 6 plus 4. That will give us 2,4. Sorry, 2,4 ohms. Okay, let's say that is 2,4 ohms. Let us find R parallel 2. Sorry, R parallel 2. R parallel 2 would be R parallel 2 would be it would be R4 times R5 over R4 plus R5. Okay, which is R4, it's 3 times 3 plus 3. That should give us 1,5 ohms. So meaning which is no 1,5 ohms. Okay. The first thing now, let's say we want to determine how much current is this source supplying to this branch current. So that means we want to determine how much current is V1 is adding to this branch current, because remember this current here, let's call it I1, is going to this junction, and this current here, let's call it I2, now is going to this junction. Then they form, let's say I3, which is ngulo simfunayo na. So what we do, let's say if we want to determine how much this source is supplying to this branch current, we first have to remove the other source by short circuiting it. Meaning we're gonna short circuit this one so that you can determine how much contribution does the current that is being supplied to the source is to this branch. Okay, most that is the definition of superposition. So let's use the red color again when determine that. Let us first draw the circuit. See, okay, we have a source. Okay, okay. There we go. Okay. Okay. This is R parallel 1. Okay. 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 This is R parallel. You sorry, this is R3. My bad. Okay. This is R parallel 2. I know. Okay. Today we're short circuiting this source OV2. Okay. 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 And okay. Now let us write down the current. This is V2 now. V2. You're sorry. This is V1. Sorry, which is equals to 12 volts. Okay. OR parallel 1 we calculated, which was 2,4 ohms. Then R parallel 2 is 1, it's 1,5 ohms. And we have a current, which is the source current, esuka up, which is I1. Okay. Lo I1 split up. I figure, let's say, a contribution current. It's a contribution current of the source. Let's call it I3 and V1 to show that okay, this current I3. It's a how much current is the magnitude of the current that the source is aiding to this branch. And then ke ngoku J is iphinde kube ne-current yale source that is going in this direction. We call it I2. Hence indeed lo I2 lo I2 ukwi-original circuit is not the same as this one. This I2 is coming from this source because remember we have removed this one. We have short circuited this source. So a current, is not even part of the circuit. The only source of current is V1. Hence, I'm saying this I2, don't compare it with this one. This one is coming from the source because we have short circuited. Because what we are doing, we are analyzing each source acting separately. Okay, that is what it is saying in the definition. Okay, now that we have I've shown you the circuit and I've drawn for you the current. Now, which current do we need to find? The main current that we need to find is this one because this is the amount of current that is contributed by V1 in this branch. Okay. Okay. So how can we do that? We can first calculate we can first calculate the total. We can first calculate the total resistance so that we calculate the total current, which is I1. Then we can apply a current divider rule. Just know when you are doing a superposition, you'll always apply that current divider rule. And okay. So what we're gonna do is we're gonna calculate the ROR total. No? Okay, we see that this and this are in parallel. Okay, let us first calculate the parallel. Let's say R parallel 3. But I don't want to the reason I'm saying R parallel 3, I don't want us to confuse them with these ones. Okay, so R parallel 3 is R parallel 2 times R3 product over sum, and which is R parallel 2 plus R3. That is gonna be R2 is 1,5. R3, what is R3? 7 ohms. 7 ohms times 7 over 1,5 plus 7. Let us punch that on our calculator. That is 1,5 times 7 over 1,5 plus 7. That is going to give us 1,235 ohms. Okay, we have found RT. And we haven't found RT. I'm making a mistake. We just found the parallel section. Now we have to find the total, ne? Because this parallel branch is in series with this resistor R parallel one. That means ORT in this case is R1 equals to R1 plus R parallel 3, which is equals to R1 go 2,4, then R parallel 3, it's 1,235. Okay, find RT now. 2,4 plus 1,235. That is gonna be 3,635 ohms. Now we have found RT. Now we can find the total current, which is I1. Total current would be a voltage V1 over RT, okay, which will be uh, 12 over 3,635. The OIT, which is I1, is gonna be 12 over 3,635, which is 3,301 amps. Okay, now that you have found this current, you notice that we can find the current I3V1 that is being contributed by the source in this branch. So using a current divider rule, it's I3V1 is equals to, okay, remember current divider rule, we consider the resistance of the other resistor, which is R parallel to R3 plus R parallel to times IT. IT is I1. Yeah? Then R parallel to is 1,5 over 7 plus 1,5 times OIT, which is 3,301. Then we find how much current is being contributed by the source V1. Okay, 1,5 over 7 plus 1,5 times 3,301, which is the current that is being contributed is 582,529 milliamps. Okay, we have found that now. Now, what do we want to do now? What we want to do is we want to, now that we sorted, okay, how much current is being contributed uh, by this source. We want to know how much current is contributed by this source to this branch, and to this branch, meaning I'm gonna short circuit, because now I'm focusing, my focus is determining what effect does this source has on this branch current. Yeah, but I'm always repeating this thing. Yeah, well, this definition. Okay, that means I'm gonna short circuit this. So let us use a blue color again for the next calculation. Okay, so to determine OI3V2, we short circuit the other source, ne? We short circuit OV1, yeah? Okay, so that we find how much current is being contributed by OV2 to the branch current. Okay, let's do that. Okay, sorry. Uh, okay, uh, okay, this is R parallel 1. Okay, remember again, we said we short circuit OV1. Okay, okay, uh, okay, okay, then okay, then sibe no R parallel 2, okay, sibe no R3, okay, okay, then sibe no V2, ne? Which is 24 volts, if I'm not mistaken. Let me confirm. Is 24 volts. Okay, okay. This one is 1,5 ohms. This one is equals to 2,4 ohms. This one is equals to 7 ohms. So we have upper the source current. Let's say it's I2, then it comes to this junction and split even I3. The voltage that is the current that is contributed by this source. Hence, I'm gonna say I3 V2. Then we have I1. Guys, again, I'm gonna show you again this current is not the same as the current in the original circuit. This current is how much is contributed by this source, and okay, then this current is the amount of current that is contributed by the source in the branch current that we seek to know the total current to. Okay, so the main thing we want to find is to find ubani I3 to ubani V2. Okay, how much is how much current is this source contributing uh, to this branch? And it is definition layer, yeah, superposition. So the first thing we have to find ORT. After finding ORT, we can find the total current. Where is the total current? Is this one, and because this total current comes here and splits, and then we're gonna use the current divider rule again. So how we find ORT? Okay, we see that, okay, now this one and this one are in parallel, and okay, let's write it down. R parallel 1 times R3. R parallel 1 plus R3. Then this whole combination is in series with this resistor. Okay, plus R parallel 2. Okay, let's find the answer. Okay, R parallel 1 is 2,4 times 7, 2,4 plus 7 plus what is R2, 1,5. Then we find RT. Okay, let's punch that on our calculator. 2,4 times 7 over 2,4 plus 7. Okay, plus 1,5. That is RT is equals to 3,287 ohms. Okay, now we found RT. We are able to calculate OIT, which is I2. The total current in this circuit is I2, so which is V2 over RT, okay, which is 24 over 3,287. We find I2, okay, 24 over 3,287. That is going to be 7,301 amps. Okay, I think I'm gonna need space in the next page. Okay, so now we found the OIT, we can use the current divider rule and find how much current is contributed by V2 in that branch. I3 V2 is equals to, okay, current divider rule. Let's go back. Sorry, current divider rule. Okay, we can see that, okay, this and this are in parallel. Yeah? So it's gonna be R parallel 1 over R parallel 1 over R1 plus R3 and times I2. Then sorry, R parallel 1, R parallel 1. Okay, what is R parallel 1? R parallel 1 is 2,4. Then R3 is 7. Okay, 2,4. Okay, 2,4 plus 7 times what is I2? I2 just calculated is 7, it's 7,301. 7,301. Okay, we find I3 V2. Okay, 2,4 over 2. Okay, that is gonna be 250. Oh, sorry. Times, sorry, I forgot to times 7,301. 301, yeah? Times 7,301. Okay. That is gonna be sorry. Can I want to punch again? Okay, let me punch. It's 2,4 over 2,4 plus 7 times 7,301, which is 1,864. Let us convert that, let us put that in milliamps, since I have put the first current in milliamps. Remember, I placed the first current in milliamps. Okay, so we divide it by, sorry, we multiply it by 1,000. 1,864 times 1,000. That is gonna be 186,4 milliamps. Okay, now that we have found how much current is contributed by V1, how much current is contributed by V2, so independently, we can add those two current. Okay, I3 is therefore equals to I3 V1 plus I3 V2, because these currents will meet in this junction and they will flow in the same direction. We add, if it was a different case whereby they flow in the opposite direction, then you would have to subtract. Guys, you would have, if this current from this source was flowing in this direction, but from this source it was flowing in the opposite direction, then we would have to subtract. But in this case, they meet in that junction, they flow in the same direction, so we add. So it's gonna be 582, sorry, 582 comma 529 plus 186,4. I3 is therefore, okay, 582,529 plus 186,4 comma 4. That is gonna be 764. You're sorry, 768, 929 milliamps. That is how, guys, we do superposition. Very simple.